Hello, my name is Ariel Cintron-Arias, and it truly is an honor to join Lathisms as one of the speakers. So, over the next few minutes, I'd like to talk to you about applied mathematics through the lens of my own experiences. But I decided that I would like to start this conversation with you telling you a little bit about myself, specifically where I come from, and things of that sort. So, my mother is from Costa Rica. My father was from Puerto Rico. I was born in U.S. soil. I was born in the island of Puerto Rico, and because of that, I am a citizen of the United States because of a birthright. Um, so I currently reside in North Carolina and I work full time as an associate professor for a public university in the state of Tennessee. I have spent various portions of time in different states. My wife and I, we like to rescue um, retired racing greyhounds, and we enjoy traveling. We enjoy um, trying out different food from different places. So, concerning my academic life, I obtained a Bachelor of Science in Mathematics from the University of Puerto Rico, Calle, and then I earned a PhD in Applied Mathematics from Cornell University. As a grad student, I had the opportunity to do research in Sandia, in Los Alamos, and as a junior faculty member, I had collaborations with aquatic ecologists at Oak Ridge. I have been in the faculty of East Tennessee State University since 2009, and in more recent years, I have become a little more involved with cloud technologies, with data science education, and injecting a little bit of computational thinking standards in undergraduate curriculum. And part of that work has to do with classes like pre-calculus, calculus, but also classes a little more upper level for mathematics majors like predictive modeling or data wrangling, things of that sort. So what we're seeing here on this slide is a little bit of some areas of interest that I was lucky to gain training as when I was a graduate student and postdoctoral research associate. Another thing that I was very fortunate was that as a junior faculty member, I was funded by the Tennessee Board of Regents, the National Science Foundation, and the National Security Agency. And they funded programs um, that had a common theme, which was workforce development by means of preparing undergraduate. Some of them were mathematics majors, but some of them were majoring in computing and chemistry. So, kind of fostering skills that had to do with these various domains that are listed in these slides at the undergraduate level. Some of those forms were projects that were formerly undergraduate research projects, but there were other forms as well. So, this is the first of six topics that I would like to talk to you about. So we're going to start with writing some equations, perhaps the most foundational mathematical model describing how a communicable disease would spread throughout a population. So we assume that a population is divided into three groups or compartments, each of which is denoted here with a little box. And one group is called S for susceptible, another group is called I for infectious, and another one is called R for recovered. We're going to assume that the total population size is equal to um, S plus I plus R. In this case, N is denoting N is used to denote the constant population size. So if we write an expression like 1 over n, This denotes the chance of running into an individual of this constant population, of this population of constant size. So this chance 1 over n also is something that we can rephrase as every individual here is equally likely to encounter each other. There is equally likely in the sense that there is no preference. And when I say no preference, what I mean is something in the spirit of uniformly at random, as in simple random sampling. So simple random sampling, uniformly at random, no preference. That's what this term denotes. So if now we're interested in saying, okay, so what happens if how many encounters can there be with individuals in group I? Every individual has a chance of 1 over n to have an encounter with somebody else in this population of constant size. So if you consider the sum 1 over n plus 1 over n plus 1 over n, keep this sum going all the way. So there are terms all the way to 1 over n. So what is this sum? This is the sum of the constant 1 over n, say when k runs from 1 through I. And so this would be equal to I multiplying the constant 1 over n. So this is basically adding over all individuals in this compartment, and this fraction now, I over n, tells us what are the chances of encountering individuals in compartment I. Now let's consider another thing here. Suppose that we have a parameter C, which denotes average number of contacts that any individual in this population has with anybody else. So if this is an average, right? So I don't know, maybe it's the same in that sense, the average is the same for everybody in the entire population. How many of those contacts are actually spent with individuals in I? Then this is where we could write an expression C times I over N has precisely that meaning. The number of average contacts spent, this would be contacts on average spent with individuals in I. So let's now consider the quantity C times I over N multiplied by a probability Q, where Q denotes the probability that given a contact, that contact is leading to an infection. So then suppose that that product of the probability Q and the average number of contacts C, that we write that with a new notation, with a new parameter beta, where beta denotes the product of the probability that given a contact, that contact generates or produces a new infection multiplied by the average number of contacts. So now we have a term that looks like beta times I over N. This precisely would be the number of contacts with individuals in the I compartment leading to infection per individual. And if we now add up over all individuals in S, so we would obtain there are S of those individuals. So the product S times beta times I over N is giving us the number of contacts between individuals in group S and individuals in group I that produce or generate a new infection. And that will be used as a rate of transfer. So this would be, maybe I can highlight this, okay, and highlight it with, I don't know, with this yellow, and that precisely would be the transfer from the S compartment. So here we would have beta times, I'm going to write it beta times S times I divided by N. Okay, so the other rate that we would like to take care of is a rate of transfer between individuals in compartment I to compartment R. We can assume that there is a constant rate at which individuals that become infectious Eventually, they develop immunity and they become no longer infections. They are now into this compartment or state called recover. So you can write that with a constant gamma and write a transfer rate of gamma times I. So we are going to write rates of change for each compartment. The rate of change of recovery of the recovered individuals is given by that constant gamma times I. That's precisely what we had, how individuals are coming into that compartment R. So let's write the rate from S to I. That's going to be a negative term. So this would be beta times S times I divided by n, and that is negative, is a loss for the compartment S, but is a gain for the compartment I. So that um, rate appears here as positive, and then the loss of this compartment would be negative gamma times I. So these three rates of change, these three derivatives define perhaps the most basic epidemiological model or the most basic mathematical model describing the dynamics of a single outbreak. So let's just sketch here what each of these functions of time would look like. The compartment R as a function of time, here is time, and here would be R of t. This is a function that's always increasing, and eventually this is going to settle at a constant, like a saturation level. Um, then the compartment S is going to look as a function of time. So here is time, and here is S of t. This is a function that initially is decreasing and eventually is going to settle at a saturation level. But the infected or infectious as functions of time. So here is the time, and I of t is a function that initially grows up to a maximum level and then it decays. So this kind of looks is completely a coincidence, but this kind of looks like a bell shape curve, and perhaps of particular interest is what happens in an initial time here, so where there would be some type of exponential growth. That's why we call this an outbreak of or an epidemic, because the number of infectious individuals would follow an exponential trend initially. So I just want to say a couple of things here. Look at that derivative for I of t. If you pull gamma as a common factor, now you have a coefficient, I is also a common factor, excuse me, and you have a coefficient for that I of t. That depends, S is a function of time, but if you make an assumption here that S is almost n, in some kind of limit, or evaluate S at n, so then this differential equation looks like a constant multiplying I, and that constant is basically beta over gamma minus 1. So this means that the ratio beta over gamma, when that exceeds 1, when that is bigger than 1, that's when that's kind of what's happening in this window here. Beta over gamma exceeds 1, and if beta over gamma is less than 1, then I of t would be a decreasing function. So in that initial interval of time when there is an exponential trend, I of t is an increasing function, that's when you expect that this ratio beta over gamma would be bigger than 1. Now let's talk a little bit about supervised learning. The one main distinction between supervised learning and unsupervised learning is that in supervised learning, there is always a target. So in this case, the target is going to be, let's see, the target is going to be this. This is what we're going to consider the so-called target. The other terminology for target is label. Okay, so in this case, we assume that the observation, which is the target of the supervised learning, is a result of something that is an outcome of the mathematical model. So this would be directly related to SIR, and also something that is basically compounded or subject to error from some measurement procedure, protocol, or device. And so there are specific statistical assumptions for the measurement error. This is the methodology. So in this formulation, we're assuming that the target, the output of the model in this formulation for the target is the number of infectious individuals. And everything here is relative to this parameter theta. So theta 0 is going to be beta sub 0, gamma sub 0. These are specific values for the transmission rate and the recovery rate. So um, this is the mathematical model. We assume that theta contains two parameters, and one way of uh, basically what we'd like to do is to find solutions of this problem, which is an optimization problem, minimizing the sum of squares as a function of the model parameters, right? So this solution um, will be called theta hat, for example. That provides a value of beta hat and gamma hat. This is just notation, but these are the so-called parameter estimates. So just to kind of put everything in perspective, this terminology of learning is what you can think of this as a regression exercise. In this case, is not a linear regression, is very nonlinear. If we think of the solutions of the differential equation as they are functions of time, but they are also functions of the parameters. So everything here, I is one of those, but so I is a function of time and it has a parameter theta. If we think of the solutions of this differential equation in terms of theta, this differential equation is very nonlinear, and as a function of theta, that will still be true. So this involves computing those solutions and then matching those solutions to the measurements, to the data. Okay, so when you're doing learning, supervised learning, you have data that is called training data, that is testing data, and ultimately you'd like to train them all. Think of train as feeding, that exercise of feeding data or feeding models to data. What you get back is usually parameter estimates that you can use to make predictions. That is the goal of supervised learning, making predictions, in this case of the number of infectious individuals. So let's now run some code simulating or computing simulations of this mathematical model for the spread of infectious diseases. So what we're seeing here is a Jupyter notebook running on an R kernel. So on the upper right, you can see the R over there. So if you are familiar with this type of, you could also run this on RStudio. So I'm going to run every individual cell here. So the first thing that you're seeing there on the screen has the coded expressions for the rates of change. So for example, there we have the expression using a highlighter that is the expression for the derivative of s, and the second expression there. So here, this would be like the derivative of s with respect to time, and then the second expression here would be the derivative of I with respect to time, and then the third expression is for dr, derivative of r with respect to time. So that's the most important part. That is coded as a separated function. It takes right now it has three input arguments. This is how this implementation is set up to function. Perhaps the most important packages or libraries here are going to be DE-solve, that has the solver for differential equations. GA stands for genetic algorithm, and Outbreaks is a library or package that contains multiple data sets. So let's now run the next cell, which produces a visualization of in this case, the data set that will be used for this demo is these are measurements about the flu, influenza. This was an outbreak in 1978 in a boarding school for boys located in England. So the data looks like the horizontal axis has the time steps. I think these were units of days. And then the vertical axis has the new cases of infection. And so here is the part that seems very convoluted, especially if you're not familiar with this code. Um, Basically, the most important part here is the sum of squares, and so the model is going to be parameter estimates here. The parameters of the differential equation will be obtained by calculating approximate minimizers of that function. The sum of squares is a function of the model parameters. So the algorithm to do that optimization is an evolutionary algorithm called genetic algorithm. So that is formally considered a global optimization algorithm. Um, these are stochastic. Think of this as like Markov chain Monte Carlo, that MCMC type of thing. These are computationally intensive. So this hyperparameter max ether, this is supposed to be in the hundreds or thousands or tens of thousands. Here, I just need you to see what this looks like with one run. So I'm just doing kind of like a toy example with that value being 5. This other parameter, population size, is the population of the genetic algorithm. That should probably be bigger as well. But with just to test what the code looks like. So what we're seeing here in blue are the observations, and that other shape over there are the predictions, the model predictions. So it's predicted versus observed. You can see that in some cases that aligns very well. One of those points is almost on top of the other. In the other cases, they are, well, the discrepancies are precisely what are considered residuals. So there is a little bit of sampling here. Again, this value 15 should be perhaps thousands or hundreds of thousands, but for the sake of for this running in less than, I mean, in order of seconds to minutes, so we can see something on the screen, then I'm executing this with a very small number over there. And so what we're seeing here, the data points and the gray curves are basically a cloud, an uncertainty cloud. Each of those curves is a prediction, and they are obtained based on bootstrap sampling. So there's a bootstrap sampling over residuals with simple random sampling. So out of this type of sampling, one can come up with estimates of the parameters and also estimates for the so-called standard errors. So here, let me see, 1 second. So the parameters in the notation of the model are beta, approximately here 1.72 or 1.7, and gamma 0.47. And so if you consider the ratio of those two values, this would be a very kind of brute force um, estimate of what the ratio beta or gamma would be, something approximately in the order of 3.7. So one convenience of having this approach of bootstrap sampling is that you're able to determine estimated values for the parameters, and also because out of that sampling, you also come up with estimates for the standard errors, and this is in the spirit of providing some type of confidence interval or uncertainty bounds around each of the point estimates for beta and gamma. So another thing I'd like to discuss with you has to do with visualizations of data or creating graphs from data sets. One of the courses that I teach is an undergraduate course for mathematics majors that basically I have modified that course to be more about data wrangling. When you are using data wrangling methods, uh, basically what you're doing is you start with the raw data and you perform transformations. Some of the transformations have to do with cleaning the data, for example, dealing with missing values. But sometimes the data in raw form is messy, and the first transformations are to transform the data set into tidy data. Well, in the process of transforming the data, it's very useful to have snapshots, to take subsets or slices of the data and create visualizations. You need to have a basic understanding of what the data is. And this is where the visualizations could be very useful. So I want to just share with you some really tiny bit example. In 1986, in January of 1986, NASA launch a mission that was called the Challenger. The Challenger was a space shuttle, and unfortunately, in after less than 2 minutes on the air, there was an explosion, and there were no survivors. All members of the crew passed away. So later, it was found that the main cause of the explosion, had to do with damage in some parts called the oil ring. These are like the gaskets that were sealing the rocket boosters. You can see the Challenger, the space shuttle was attached to some rockets, and that was used to lift the Challenger onto the space. So there were initial tests that engineers had performed, and this is an example of what the report of those tests looked like. Some engineers had reported that there was evidence of damage on the oil ring, and there was some relation to temperatures, environmental temperatures. What you're seeing on the right side of the slide is another way um, of viewing the same type of information. So here is a scatter plot where you have temperature on the horizontal axis and a quantification of damage to the oil ring on the vertical axis. So this is a very basic exploration. You have two quantitative variables and you like to establish if there is a relationship between them. In this case, there is a relationship. The data points we see in the scatter plot are not the original points. They have been transformed with smoothing functions, but nevertheless, a curve, which is a regression, nonlinear regression, can be calculated to kind of establish that these points, the damage to the oil ring, depends in a decreasing fashion. In a decreasing fashion, is dependent on the temperature in a decreasing manner. So if you for larger temperatures, if you increase the temperature, then the damage goes down. But what was more pertinent that day, the day of the accident, was that the environmental temperature was about 30 degrees. And with this at hand, the forecast for the damage, you can see 30 degrees, that would be basically somewhere around here. So the damage for a temperature as low as steady, the damage was expected to be really, really substantial. So this type of information, had it been available at the time, a very simple scatter plot, very simple exploration of relationship between two quantitative variables would have provided very, very useful insight. So in my class with the math majors that are learning how to code in R and how to code in Python, I do spend some time with data visualizations. I would say that I use these books and I would recommend them to anybody if you want to have some type of traveling reading. The visual display of quantitative information. It's a really good, it's a must read. The Draw to the Wind, also very easy reads. Both of those books are non-technical, and then the books you see on the right, they are more technical. They're published by Springer. The Grammar of Graphics. If you have ever seen or used ggplot, one of the libraries in R, the GG of ggplot stands for the Grammar of Graphics. Unsupervised learning is a domain that has to do with algorithms to identify patterns in the data. There is no target or there is no label in unsupervised learning. So I want to motivate to give you a sense of what unsupervised learning and pattern identification is about. I have a couple of illustrations, but first, let's imagine we have a tabular a data set that is in its raw form is stored in a table. So it has tabular form. And the table has three columns. Each of these columns may be considered a field or a feature. And we have information about a year, information about a state, one state of the United States, and some value count. So because there are three columns, it would be natural to think of a visualization of this where one axis has year, another axis has the state, and another axis has the counts. Okay, so three-dimensional, three columns, three-dimensional. But instead of doing three dimensions, so forget three dimensions, um, one uses a different. Basically, you have three dimensions and you want to only operate with two dimensions. So this would be something that has the year on the horizontal axis. It has the state on the vertical axis, and the dimension, the information about this column of count is there is a color code. Okay, so you use some kind of color to keep track of this way of visualizing. So this is usually called a heat map. It also may be referred as a plot, a heat plot. It's a way of coding three-dimensional information into two dimensions. The colors are very, very important. So now let's examine this visualization we have on the screen. A couple of things here. On the horizontal axis, we have time units in units of year. On the vertical axis, we have locations. This would be considered categorical data on the vertical axis, where the categories are, each category is representing a location, a state. So there are 50 of those locations. And then there is a representation in terms of values. This would be number of cases of some disease. And there is a spectrum here. So you can see that the colors, a lot of colors here, but there are some extreme colors in terms of the dark versus light. So the darkest is like a dark purple. There is kind of an in-between green, and then there is a light. It goes in the scale to lighter green and then yellow. Okay, so values that are very yellow, those would be the smallest values. Values that are very dark purple, those would be the largest values. So this visualization is interactive. It means that as you change the cursor, you place the cursor in a specific location, then you can see information about the graph. So for example, Wyoming here is at the very bottom. So if I'm going to position, I don't know, right there around 1940, so we can see a display of the year, the value on the horizontal axis corresponding to the value in the vertical axis, Wyoming, and then the count, 393, basically 394, right? And so we compare that for Wyoming at 1981, for example, very small number versus that other number. So there is a contrast. Let's say Rhode Island here in 1932 um, has 473 cases, for example, and Rhode Island in, I don't know, 1979 has almost 11. Okay, so that part of why we're visiting or reviewing this visualization, it is interactive. There is an event that is represented here in as a yellow vertical line. That event occurred in 1963, and that event is the introduction of an immunization. So this is a disease for which there was a control measure, a vaccine that was introduced at a specific time point, and then this allows to display a change in pattern before and after the event. And at a quick glance, you can see there is a lot of dark before 1963, and there is a lot of lighter colors after 1963. So that is the year in which this immunization was introduced. There's kind of more information here. So in 1963, the year in which vaccines were introduced. And this type of visualization is called heat plot or heat map. Basically, you are taking three dimensions and displaying them in two dimensions. So year on the horizontal axis, state on the vertical axis, and there is a color code for the values of number of cases. That's kind of um, what brings these color patterns. Text vectorization has to do with data that in its raw form is text data, and this data is transformed from text into some type of numerical representation. Usually, algorithms um, require numerical values, so this is a very important transformation. So what we're seeing here on the screen right now is let me tell you a little bit about where this data comes from. So this is one conversation in a contact center for a public utility company. So in the contact center, there are specialists taking in calls, and the person that is calling usually has a problem. The specialist at the contact center is trying to find solutions for that problem. So that conversation was one data set, and you could go over the words in the conversation, and you could come up with these bar plots here representing how many times a word was used in the conversation. You see at the bottom there a very long bar that was corresponding to a word that was used many times relative to all the other words. So another representation, you could keep these counts, these frequency counts in this bar plot representation. Another common visualization is what's called the word cloud, where the words are represented in size and intensity. As far as the bigger it appears, and the more thick the font size appears, then the more presence the more frequency the word has. So that's what way I represent two ways of representing this data. Now, in this case, there were five conversations. So that information was put together in this type of matrix. This matrix is called document term matrix. So you can consider each conversation one document, and each term is a word. So you can call it conversation word matrix or document term matrix. So along the horizontal axis, you collect all words used on these five conversations. It's like a vocabulary. There's more than 400 words in this case. And then the vertical axis keeps track of how many documents how many conversations. There were five of them here. What is displayed in this representation? This is another illustration of a heat map or heat plot, where the color intensity, there is a scale, the darker the blue, the higher the number. Light blue or white represents really small numbers, small values. So words that appear with really dark blue here means that are words that are used a lot across conversations. So from this type of heat map, um, one would wonder between this illustration of this heat map and the previous illustration where data, the nature in raw form data come, they are very different data sets. But once the data is represented with this visualization, one may wonder if there are additional patterns or additional relationships that are not so obvious. And that is one area in which unsupervised learning algorithms are very useful for. One of those algorithms is called k-means. The means here stands literally for what that word um, stands for. It's average. Specifically, this is going to involve average in the sense of something that's called centroid. So the data sets are going to be subdivided or explored to identify communities or groups or potential clusters, and some of those calculations have to do with calculating average between subsets of data points. So this description of the k-means comes from one of the textbooks I use. It's an open educational resource, and I use this textbook in my linear algebra class. Now let's work with an illustration of this algorithm called k-means, which is an algorithm used for unsupervised learning. And this is in the context of identifying when data may have patterns that exhibit some type of structure like communities or groups or clusters. So here's an illustration with a data set that has 177 points. One of the hyperparameters in k-means is that value of k. You could argue that here, at the very least, there is one cluster in this location. This is a two-dimensional plane, so this is a cluster that's kind of in between the second quadrant and the third quadrant. So if you were just going to be very extreme and say two clusters, these clusters, that cluster, and then everything else, this could be one way of identifying two groups or two communities there. Another maybe way of subdividing this or identifying groups could be this being one, maybe there's one over here, and maybe there's one over there, another one. So that's one, two, three, four. You could say five or six, depending on if you consider that's one whole community over there, right? So with different values of k, so this would be for k equals 5, with different values of that hyperparameter, then there would be various clusters. This is what we're going to illustrate next. So suppose that we're going to be a little radical and say that there is only one cluster. Okay, so k equals 1. So if that is the case, um, the representations here will have colors according to the number of the according to the values of k. Here you see most of this all of the data points in red, but there is one point that appears in the middle. This point here, that is the um, so-called average of points or centroid, right? So this is the so-called it's kind of like the center of the data, or the centroid is the average of all these data points. So when there are more groups, the centroids will be in this visualization, this illustration. The centroids will be identified as fill-in circle with color black. So let's be a little more extreme and say that instead of one, there are as many as 11 groups or 11 clusters. So you see that there is a color code, a different color representing each cluster, of course, and then there is that black dot, solid black circle appearing. That is in the middle of, that is the representation of the average of those data points for each of those clusters, right? And so let's just go back to something more like maybe there is only two groups or two clusters. Actually, I had argued that the one group of points in the second and third quadrant, that would be one, but that's not what the algorithm decided. So it splitted this into two groups in this fashion. So And what if there were as many as maybe six? What would this look like? Still is six clusters over here. I think maybe this would be more between three and five, but let's do three clusters. Yeah, and let's do just five for the sake of verification. What that split with fibers would look like. So, in summary, K-means algorithm is a common algorithm for unsupervised learning, is helpful in identifying communities or groups. Presumably, these are sets of points that have things in common. That is determined. So there is the centroid is a measure, is a quantification of the average within the group, and there is a way, there is a need to have a metric that measures distance, comparing pairs of points at a time, and therefore allowing a threshold to be implemented to identify if a point is sufficiently close to another point to therefore be classified as a member of a cluster. So this type of algorithms, k-means, is used in scenarios like the ones we discussed before, where we would like to further explore if there are relationships or patterns in data sets that may not be obvious at first glance. I want to share with you some of the skills I have in educational technology, which I have listed here. Um, in fact, I'm talking to you by using my skills in Camtasia, which is one of the programs I use for editing videos. In recent years, I have been more involved and more interested in adaptive learning. For example, this tools for adaptivity can be very useful in offering alternatives for assessments that are, especially in mathematics, traditionally exams are summative assessments, and using some of these digital tools with adaptivity features could be very innovative. And about 4 years ago, I became an ISTE certified educator. ISTE is the International Society for Technology in Education. The UDL stands for Universal Design for Learning, and computational thinking. Those are very important areas that influence my practice of mathematics at the college level. So all these educational technology skills I am sharing with you because I am um, involved with distance learning. So far, I have created 12 online courses of college level mathematics, which are listed here. Seven of them with fully asynchronous delivery, and five of them with live video streaming. So, and I'm just sharing this with you because, when I started doing this, um, there were some of my colleagues, there were mathematicians that told me this is not how you teach mathematics at the college level. They were not using the same words, but basically telling me that it had little value. And I wonder how they would feel if I go around and tell the number theories or the algebraists or the statisticians something to that effect, that the Bayesian statistics or the prime numbers, that has little, your research has little value, your activity, your scholarly activity. And in that case, there was a little tension there, office politics, if you will. But here I am, 12 classes later and counting. So sometimes you take the advice or the words the best you can, and you just keep working. And if you find that you have passion for that, or if it's worth your time, you just keep diving in, because this has allowed me to grow professionally in several dimensions. So as far as online learning, um, and as far as computational thinking, as far as educational technology, that has, in my case, in my practice, is propagated in many senses. So here's a quick representation of what my classroom used to look like several years ago. I used to operate in a classroom that is considered brick and mortar or on premise. there were a few computer stations in that classroom. Um, Typically, I would write on a blackboard with chalk, or on a whiteboard with markers, or on a glass board with markers as well, magic markers. And then eventually I evolved into using tools that are web-based or cloud-based. I use Desmos on a regular basis, Microsoft 365, definitely Jupyter notebooks running Python or R. And so these are uh, basically substitutions of that on-premise classroom. And so when you get involved with this type of educational technology, you have to keep in mind this is a really good illustration. If you look at the left side, there is a fence, and there are accommodations made for every individual. Now, those accommodations, one of these individuals doesn't need them, and another individual, here you look at the middle graph, another individual actually needs double of the accommodations that are given to everyone, right? And so that would be a scenario in which the accommodations work. But if you rethink and reformulate and perhaps use a fence that is not made out of wood, a fence that allows seeing through, that is exactly the design that is universal. It serves all populations. And that brings me to a very important area of educational technology called universal design for learning. So this has to do with how you convey the information. And for us mathematicians, especially teaching really any level, but teaching in higher education, commonly the information that we are transmitting is complex, is heavily complex, is loaded, and then we have to deal with some people actually arrive and they are afraid, scared. They say they don't like math. So, universal design for learning has to do with activating certain parts of the brain to trigger activity and make that exchange of information optimal. One of the things that has to do the most with our area, mathematics, is this subdomain of representation, activity in the back of the brain. So things about supporting how the information is displayed, um, decoding mathematical notation, decoding text, decoding symbols, perhaps highlighting and exploring patterns and critical features, and definitely exploring relationships. So I want to share with you something. This is a really tiny example. I teach linear algebra. What you're seeing on the screen is a snapshot of what I wrote in one of my lectures. You see at the bottom there is a formula that involves the inner product or dot product between vectors x and y and norms of x and y. And then on the left side is cosine of the angle between these vectors. So when I was writing this in during a live session, I was using digital tools. I made a point to write in more than one color. I'm using the colors um, in actually different intensities as I use one color to write, and then I use other colors for highlighter, and I'm trying to very diligently, I'm trying to align this. There is an intention here, which is that universal design for learning. So in that same class, students take an assessment, they turn in an assignment at the end of the week, they have a little quiz about that same formula, but I have them work on another type of assessment. This is an assessment where they use colors. Um, they use colors from the so-called color wheel to select the red, green, and blue codes, the RGB codes, representing. So now they work with vectors representing colors. And there are two scenarios. We're going to see this in just 1 second. They're supposed to work in two scenarios. So they choose one pair of colors. So this is the color wheel, and this person selected two blues and selected one blue and one red. So with the two blue representations, they're working on one pair of vectors, and they compute the angle between the vectors, both in radians and degrees. And then they move on to the other scenario, where the two vectors representing two very different colors, compute the angle in degrees and radians, and then they report their findings. So this is an activity where they're working with that formula, and this is an activity that's aligning with all these different principles about decoding notation, exploring patterns, definitely exploring relationships, and so on. So over the last 2 years, I've been more involved with responsible artificial intelligence. And I want to tell you a little bit about what responsible AI is. This is also sometimes referred as machine learning, responsible machine learning, or artificial intelligence and ethics. So it definitely has to do with how data may be misused. So just to be clear, artificial intelligence relies on data, is the input data, is the lifeblood of this type of technologies. So there is a very traditional principle for people that work with data, which is garbage in, garbage out. So the quality of the outcomes may be compromised based on the poor quality of the input data. And so it's very important to evaluate and control um, the potential bias. And so when in this context, bias means basically with preference. So when data is unbiased, it means there is no preference. So and some of the mitigation techniques and methods to control bias have to do with statistical sampling methods to at least reduce the potential of preference in some scenarios. So there are criteria to define when something is fair. So here, fair is going to be analogous to no preference or unbiased. As what you see here stated is something that use this terminology of true positive and false negative. So I want to give you a sense of where that comes from. This table, which may have too much information. So this is a table used for data that's categorical. So in this particular case, what's represented here is two categories. One represented with the value of +1 and one represented with a value of -1. These are categories. Each category represents a class. The type of this would be the type of mechanism used to assess how a model for classification is performing. Okay, so let's just review what's part of what's stated in this table. So the columns are taking care of the predictions, the rows are taking care of the observe. Here they're referred to as true. So suppose that we keep track of the prediction of +1. Something is being predicted as being +1, and it is observed as +1. So this entry of row 1, column 1, this entry in that table is considered true positive. If the prediction is that something is predicted as -1 and it is observed as -1, now we're looking at the entry on row 2, column 2. Both of those entries are the diagonal entries of this 2 by 2 matrix. So that's a true negative versus what the first defined as a true positive. Anything that's off the diagonal would be the misrepresentations, miscalculations, the errors. Everything that's predicted as a -1 yet is observed as 1. That's a false negative. Anything that's predicted as +1 and is observed as -1, that's a false positive. So this is a way to quantify whether a classification model is making errors or making mistakes. This is a matrix called the confusion matrix because commonly is used to assess how confused a model might be. And so this terminology of true positives, false negative rates, it comes from this context. And so the fact that here there is mention of one definition of fairness in terms of this terminology, this is in that context of classification this is called binary classification. Okay, so I just wanted to give you a sense of what this field, this domain is about. Um, I have used materials, open education materials provided by Amazon Web Services and their Machine Learning University. I have used some materials from an organization called AI for All. These are open and free. And then there are case studies, very useful case studies. They're fictional, but they're very useful to promote, you know, guided conversations, dialogues about AI and ethics that they are provided by Princeton University. So recently, I have been working with a collaborator in putting a proposal for an undergraduate course in responsible AI. If that proposal is approved, I will be able to teach or co-teach this at a different institution, not my home institution. At East Tennessee State University, I have implemented versions of this within a course that used to be called mathematical modeling, and in recent iterations under my uh, with me as an instructor, that course has evolved into an undergraduate predictive modeling course. So this would be a good time for me to thank you once again for your kind invitation and for having me as a speaker. And I want to share with you that for much, for most of this presentation, this was the scene. This was the look behind the scenes over here. Three greyhounds in red is Romeo, in blue with a blue jacket is Luz, and with a black jacket is Mace. And they were also attending my presentation for Lathisms. I truly it was a pleasure and an honor to share some of my experiences with you. I would say that data literacy is at this point in the 21st century, as educators for as instructors in higher education. Data literacy is a must. So we are usually, as mathematicians, in charge of quantitative skills or critical reasoning, but computational thinking, algorithmic thinking, and data literacy, those are skills that we need to make sure that we propagate these skills with our undergrad students, whether they're service courses, general education courses, or in major in discipline courses. These things need to be part of our toolbox. Our students in general, our undergraduate students, need digital literacy as well. So, digital citizenship, digital literacy, these are also tools in general. Basically, that's my opinion and my experience. And I think it would be really strange for a university, especially a public university, in the 21st century, to avoid distance learning. So I think e-learning it's something that it's very in the stage in which we are in this explosion of generative AI. We really are experiencing some activity, and we have to, perhaps more than just e-learning but higher education, we need to come to terms and make sure that we find ways to have generative AI work for us as educators and not against us. So that's kind of my speech. I want to thank you again for listening, and goodbye.